Our goals in this lesson, two of them. First, to be able to identify segments and lines that are related to circles, and then to use properties of tangents to circles. Our first goal, to identify segments and lines, this will be a whole lot of new terms that we need to learn today. And then use properties. These properties will allow us to solve some problems in our circles. Here we go. You should have already filled in your terms. A circle. A circle in your own words. Kevin, what did you say it was?
Set of all points in the plane that are equidistant from a certain point.
That's it. A circle is the set of all points in a plane that are equidistant from a given point. And that given point is called the center. If this is the center of my circle, and the circle is all these points that are the same distance or equidistant from that center point. What do we call that distance from the center to the circle? It's called the radius, which was your very next term. So a circle, in a circle, all of the radii would have to be exactly the same length, because the radius is that distance from the center of the circle to the edge of the circle. We need to talk about one more thing before we leave this slide, and that is how we name a circle. Circles are always named by their center point. Okay, so you want to add that into your notes here. Name a circle by its center point. Since the center of this circle is labeled point C, then we would name this circle Circle C. And you will see notation like that in your notes, in your homework, on tests and quizzes. You need to recognize that when they draw a little circle symbol with a dot in the center of it, that's the symbol for circle, and then they will put some point after it. If they said circle P, then they're telling you that that's the center of that circle that they're discussing is what? They say circle P, the center is point P. Nope. Congruent circles. Congruent means the same thing that it has meant all year long. What does it mean to be congruent, Tiana? To have the same measure. Okay. Well, we measure circles by their radii. Radii is plural for radius. Okay. So congruent circles would be two circles that have the same radius. Two circles that have the same radius. If I had these two circles and I were to measure the radius of each circle, measure the distance from the center of this circle to its side, and let's say it was 5, and I measure the distance from the center of this circle to its side, and it was also 5, then these two circles would be congruent to each other. But let's say I measured this one and it was 5.1. Are these circles congruent? No. They're only congruent if the radii are the same length. Okay. A diameter. A diameter is a segment that goes all the way across a circle through its center point. A diameter is a type of chord. Chord would be your next term. A chord is a segment that has both of its endpoints on the circle. So this is a chord, but this is not a diameter. A diameter is one that passes through the center of the circle. Okay, so a diameter is a type of chord, but not all chords are diameters. For instance, I might ask you here to name all chords. If I said name all chords, what would you name? Hunter, what would you name if I said name all chords?
Chord CD and chord AB.
You would name segment CD, and you would name segment AB. But if I said to name all diameters, Anthony, what would you name? Segment AB. All right, chord we've already talked about. A chord is a segment that has both of its endpoints on the circle. Some chords are diameters, but not all chords. For a chord to be a diameter, review with me. For a chord to be a diameter, Brianna, what would have to be true about the chord? It would have to pass through the center. Secants and tangents are different than chords. Secants and tangents are lines. Secants and tangents are lines. How is a line different than a segment?
It never stops.
Lines never stop. Segments have endpoints, but lines never stop. Okay? So secants and tangents, they are both lines in our circle. The difference between a secant and a tangent is how many times they intersect the circle. A secant intersects the circle how many times, Kevin? Did you get that far in your terms? You should have written your terms. A secant is a line that intersects the circle twice. Tangent, Tyler?
Intersects the circle once.
Only intersects the circle once. So secants and tangents. Secants and tangents are both lines. So I'm going to draw a couple of lines. We'll call this one line L. And I'll draw another line down here. And we'll call this line M. Okay. Line L. Secant or tangent, Dion? It's not tangent. It intersected the circle twice. Line L is secant. Line L is a secant because line L intersects the circle twice. Okay? So line M would be what, Dion? Line M would be a tangent because line M intersects the circle one time. It's not until a little bit later in your notes that they introduce what this point is called, but since I have it drawn now, I want to go ahead and talk about it. This point where the tangent line touched the circle, I have it labeled point D. It has a very specific name. Since it's the point where the tangent line touches the circle, it is called the point of tangency. Okay, so a little bit later in your notes, we won't have to discuss that again. We've already talked about a point of tangency. A point of tangency is the point where your line intersects the circle, where a tangent line intersects the circle. All right, tangent circles. Tangent circles are coplanar circles that intersect in one point. Tangent circles. They are coplanar circles that intersect in one point. Like in this diagram, these two circles intersect at one point here. They are tangent to each other. This is their point of tangency, this point where they intersect each other. What about these two circles? Are they tangent? Why not? They intersect at two different points. Okay, so those are not tangent to each other. What about these two circles? Yes, they are tangent. There's one point where they intersect each other. They have a point of tangency right there. Okay, so tangent circles. They are coplanar circles that intersect in just one point. Concentric. Concentric circles are circles that are coplanar and have a common center point. In other words, they have the same center point. Kind of reminds me of a dartboard. Dartboard has several concentric circles. What is the center point of those concentric circles? The bullseye. Okay, so it kind of looks like a dartboard. Okay, it's more than just one circle being inside of another. Are these circles concentric? No. Okay, the center point of the larger one is about here, where the center point of the smaller one is about here. They do not have the same center point, so these are not concentric circles. Concentric circles are circles that have a common center. All right, a common tangent. A common tangent is a tangent line that intersects two circles. A line or segment that is tangent to two coplanar circles. Over on the side of your notes, you're going to need to add this diagram, and we need to talk about there are different kinds of common tangents. There are what we call common internal tangents and common external tangents. And on your next test and quiz, I'm going to ask you if the tangents are common internal or common external. In your homework tonight, you're also going to have to answer questions like that. I could draw a tangent to these circles across the top, like this, so that it intersects this circle one time and intersects this circle one time. This is a common tangent. I could draw another common tangent across the bottom here. You should be drawing these into your notes, please. Okay. These tangents are called common external tangents. Common external tangents. They're called external tangents because while they connect the two circles, they do not go between the circles. Change the color of my pen here so we can see the difference a little better. If I were to start here at the top and come down tangent to this circle and then go across and be tangent to that circle so that I have a point of tangency here and a point of tangency here, this is also a common tangent. I could draw one more from the other side, tangent to this first circle, and then tangent to the second circle. So I have a point of tangency here and a point of tangency here. These tangents that I've just drawn in yellow, these are what we call common internal tangents because they pass between the circles. Okay, so common tangents. There are what we call common internal tangents and common external tangents. And you need to be able to distinguish between the two. Point of tangency we've already discussed, so I won't spend a lot of time here. Remember, a point of tangency is just a line. It's the point where the tangent line intersects the circle. So let's move on to our next term. All right, interior of a circle, exterior of a circle, and we need to add one more term, on. There are three positions when we're dealing with a circle. There's the interior of a circle. That's all the points that lie within the circle. Exterior of a circle, that's all the points that lie on the outside of a circle. But there is one more position that they do not mention here, and that is on the circle. So you need to add that into your notes, on. The interior of the circle would be all the points within the boundaries of the circle. Let's put a few points on the circle. All right. If I were to ask you on a test or quiz or in the homework to name a point on the interior of the circle, Christian, what would you name? Don't listen to your fellow students. Look yourself in the circle. Name a point on the interior of the circle.
A.
Point A is on the interior. Is that the only point on the interior, Joey?
No.
What's another point on the interior of the circle? A is the point that Christian named.
Obviously, B.
B is not on the interior of the circle. It is not on the inside of the circle.
Come on, man, use your head.
Anthony, what's the other point that's on the interior of the circle? Point C. Points A and point C are on the interior of the circle. Name a point on the exterior, Grace. Point D. Point D is on the exterior. And then on. On is a third position that we need to be familiar with. On is all the points on the actual line here that make the circle. So a point on the circle would be which point, Tiana? Point B. Point B is on the circle. Okay? It might not seem so important right now, and it may seem like common sense, but later in this chapter it's going to become extremely important that you can identify where the points are. Identifying where the points are at will determine which rule you will use to find the measure of your angles. So, moving on. All right, in example 1. I just paused the recording to remind you that I am recording, so all of your discussion that you just did is on my recording, and I cannot take it off. So it will be on Facebook when I post it to Facebook tonight. And when your parents, I'm going to specifically say that this was 4th hour. So then when your parents will know that it was your class.
And my parents don't get on Facebook.
Huh? I may just send your parents an email and say, please watch the video of 4th hour today. Let's don't have any more interruptions. Okay? Here we go. Shh. I'm about to unpause. Example 1, identifying special segments and lines. In your homework tonight, if you were given this problem, I would expect you to draw this diagram one time and then use it to answer the whole set of questions. Tonight in your homework, there may be 8 questions that go to one diagram. You would draw that diagram one time and answer all 8 of the questions. You would write down the original question, and then beside it, tell me what the segment is. Here they want us to describe the segment as a chord, a secant, a tangent, a diameter, or as a radius. So look at your diagram. Segment CG. Segment CG begins here at the center and goes to the edge of the circle. Anthony, what is segment CG?
A radius.
Segment CG is a radius of this circle. Because it began at the center and went to a point on the circle, it is a radius. Okay? Segment EG. Segment EG is this segment that begins at point E and ends at point G. Miranda, what is segment EG? It is a kind of chord, but is a very specific kind of chord since it passes through the center. A tangent, remember, is a line that intersects the circle twice. We want the chord that passes through the center. John?
Diameter.
It would be a diameter. All right. Notice that the symbol changed. It's no longer a segment. What does this ask us for? This asks us not for array. It's got 2 arrows on it. This is for line AD. They want to know what is line AD. Ryan, what's line AD?
It would be a tangent.
It would be a tangent because it only intersects the circle one time. Okay. Tonight in your homework, you only need to give the explanation. If it asks for the explanation, there are some questions it will ask you to explain, so pay attention to your directions. All right, couple of theorems that we need to discuss here. These theorems will help us to find measures in our circles. The first theorem says, if a line is tangent to a circle, remember the part of the statement after the if? That's called your hypothesis. That's your beginning condition. That's what you have to have. So to use this theorem, what do we have to have, Hunter? We must have. To use this theorem, what must we begin with? What's our beginning condition? Right here.
If a line is tangent to a circle.
We must have a line tangent to a circle. How will you know, Daniel, if you have a line tangent to a circle?
There will be 1 point.
It will only intersect the circle at 1 point, like this line does. So we have a line that's tangent to a circle. According to this theorem, when you have a line that is tangent to a circle, then it does something. What does that tangent line do? It is perpendicular to the radius that's drawn to that point of tangency. So we have a radius here that's drawn to that point of tangency. What does perpendicular mean, Mackenzie? That it forms a right angle. Since that since that radius is drawn to that point of tangency, it will form a right angle there. If line L is tangent to circle Q at point P, then line L will be perpendicular to segment QP. Now, how's that going to help you in your homework? Tonight in your homework, you're going to have diagrams similar to this, but they're going to draw an extra line right here. And maybe they will give you this portion of this line and maybe this portion of this line and ask you questions about this line over here. How will you find that segment? You would use the Pythagorean theorem. The thing is, they are not going to draw the right angle for you. They're going to expect you to know that if this line is tangent to the circle and the radius is drawn to the point of tangency, that there is a right angle here. And since you know there's a right angle there, then this forms a right triangle and you can use the Pythagorean theorem. So you will need the Pythagorean theorem in tonight's homework. The converse to this theorem is also true. What's a converse? Ryan?
The opposite.
The opposite, when we switch it around. Okay? In the first theorem, we knew that the line was tangent. Because the line was tangent, then the radius would be perpendicular to it. In the second theorem, you're not going to know if the line is tangent. They're going to give you problems where the whole tangent line is not drawn. They're going to just give you a piece of a line, and you're not going to know. It's going to depend on how that line is tilted as to whether that line will be tangent or whether that line is secant. They're only going to give you a piece of that line, and they're going to give you the radius drawn to it, and they're going to give you another piece over here like that, and they're going to give you numbers like 3, 4, and 5. And they're going to say, is this segment tangent to the circle? How will you find out? You will find out if it's a right triangle. Way to go, Tyler. If it forms, if these three lines, these three segments, I should say, if they form a right triangle, then this is a right angle. And this theorem says that if it is a right angle, if a line is perpendicular to the radius, then it is tangent to the circle. So you will do a test. They will give you all three measures, maybe 7, 8, 9. They'll give you all three measures. You will plug them into the converse of the Pythagorean theorem. And remember, if that longest side squared is equal, it becomes a question. If it is equal to the other two sides squared and added together, then it is a right triangle, therefore the segment will be tangent. If it's not equal, then the segment is not tangent. It's not a right angle, so it won't be tangent. That's problems numbers 36 through 41 in your homework tonight, 4 of them. You're going to need to use the converse to the Pythagorean theorem. You're going to need to do that work, and it's also going to say explain. Okay, so refer back to this theorem for numbers 36 to 41. All right, last theorem. Then we have a couple of examples, and we'll be done. The last theorem says that if you have two segments from the same exterior point, and they're both tangent to the circle, so you got to have two segments. They have to come from the same exterior point, and both of those segments have to be tangent to your circle to use this theorem. If that's true, gentlemen, if that's true, two segments from that same exterior point, both tangent to your circle, then those segments, according to this theorem, will be congruent to each other. Since these two segments, SR and ST, come from the same external point S, then SR and ST will be congruent to each other. All right, let's look at example 2. In example 2, this is an example about a fountain, and it says that you're standing out here at point R, 4 feet away from the edge of the fountain. It also says that from where you're at to a point that's tangent to the circle, that distance is 8 feet, and it wants to know what's the length of the radius. Remember, all radii in a circle have the same measure, so that segment and this segment from the center to the edge of the circle, they would both be radii of the circle, and they would have exactly the same length. From the theorem that we learned today, if a radius is drawn to a point of tangency, what's true about the radius and the tangent line? That they are perpendicular, which means they would form a right angle. So this triangle here formed would be what type of a triangle? It would be a right triangle, and since it's a right triangle, then we can use the Pythagorean theorem. The tricky part about this problem is realizing what to use for the hypotenuse right here. We know that this piece of the hypotenuse on the inside of the circle is r, and this piece of the hypotenuse on the outside is 4. Do we say that together they're 4r? 4 plus r, not 4 times r. So the hypotenuse is r plus 4, and we need to square that. They assumed that you would remember how to square that binomial. A lot of us think that that would be r squared plus 4 squared. That's incorrect. We need that whole binomial, r plus 4 times r plus 4. It's the whole r plus 4 times r plus 4. How do you multiply binomials like that? Remember FOIL? That's it. We need to do the first term times the first term, r times r. You need to do the outside terms, the r on the outside times the 4 on the outside, and get a 4r. You need to do the inside, the 4 times the r, and get another 4r. And then the 4 times the 4, the last, and get the 16. So where did the 8r that they have right here come from?
4 plus 4.
The 4 plus 4. 4r plus 4r right here in the middle, putting your like terms together. Now, they expected you to remember how to do that and how to get from the r plus 4 squared to this trinomial r squared plus 8r plus 16. Hopefully, you wrote these extra notes down here to remind yourself how to do that. Now, we have r on both sides. We don't want r on both sides, so we want to get rid of this r squared. How do we get rid of this r squared? No, I want to get rid of the whole r squared. I want that whole term gone. So I would want to subtract r squared and get that gone. But if I subtract r squared from that side, you must also subtract it from the other side. So what happens to r squared? Cancels out. Now I've got 8r plus 16 equals 64. What will you want to do next? Ryan?
Subtract 16.
Subtract 16 from both sides. So that 8r would be equal to 48. 8r would be equal to 48. Want to get r by itself. Michael, what would I do? Divide by 8. R would be equal to? R would be equal to 6. So we have our radius. The radius here then would be 6 feet. All right. Let's move on to example 3. In example 3, it is important that they told us that this line AB is tangent to the circle at point B. So that makes point B a point of tangency. And they also told us that line AD is tangent to the circle at point D. That makes point D a point of tangency. Today, one of our theorems discussed this situation, said that if we had two tangent segments from the same external point, what would be true about those tangent segments? They would be congruent. So AB is equal to AD. Plug in what you know about AB. AB is 49, and AD is the x squared plus 24. You want to solve this and get x by itself. Do what? Joey, what would you do to get x by itself? What would you do to get x by itself?
You'd have to
Subtract 24 from both sides, so it would end up with x squared is equal to 25. Now remember, this question is asking you what number can you square to get 25? What can you square to get 25? Just a positive 5? Or a negative 5. You could square a positive 5 or a negative 5 and get that 25. So this answer is actually both positive 5 and negative 5. A lot of times we can't use the negative answer because the negative answer would make the length of a segment be negative. Okay? But in this situation, if we use the negative, we would still end up with a positive answer. So we can use both the positive and the negative. Just be careful when you do get two answers like this. Be careful and check and make sure that you can use both of them. Sometimes you have to throw out one. All right. Let's look at the last example. Again, we have segments or lines that are tangent to our circle. This segment is tangent at point B, and this segment is tangent at point D. What's true about these two segments, Ezra? They are congruent. Segment AB will be equal to segment AD. Substitute in. AB is 5x squared plus 4x minus 18. That will be equal to the 4x plus 27. What would you do first, Hunter, to solve this equation?
Each of like terms. Combine like terms.
Combining like terms means that we have like terms on the same side of the equal sign. I understand what you're meaning. You're wanting to get rid of this 4x on the right-hand side, so you would need to subtract 4x from both sides. So what's going to happen to the 4x? It's going to cancel out. What would you do next, Lauren? Add 18 to both sides. Add 18 to both sides, you end up with 5x squared is equal to 45. What would you do next, Danielle? How would you get rid of the multiplying by 5? 5 times x squared. You would divide both sides by 5. 45 divided by 5 is 9. Remember, this is asking you what number can you square to get 9? Final answer here, Mackenzie. Remember, there's two numbers we can square. We could square a positive or a negative 3. And as long as neither one of them make a segment negative, you can use both. All right, open your textbooks. Let's work on the homework. Huh? I just turned off the recording.